Hello and welcome to our physics class. In chapter 4, that is moving charges and magnetism. Today we are going to learn about force on a moving charge. Force on a moving charge placed in a uniform magnetic field. So when we allow a charged particle to move in a magnetic field, then the charge experiences some force. It says like this. Let us see what type of force or what is the expression for force. Let us first of all take a uniform field. Uniform field we draw like this, parallel to each other. This side you have north and this side you have south pole of a strong magnet. Now the field lines will pass from north to south. But what we are going to study is if a charged particle, say a positive charge, it can be a positive charge or it can be a negative charge, if we allow it to move with some velocity, say v, at an angle, say inclined at an angle theta with the magnetic field. This is the direction of your magnetic field going like this. Then this charge experiences some force. First of all, let us resolve this velocity v into two components. One component, the parallel component towards theta, it will be v cos theta, and the perpendicular component, we will take it as v sin theta. So these are the two components. If you resolve v into parallel component and perpendicular component, so let me write down here like this. Let the charge be q, positive charge. Let a positive charge q be moving in a uniform magnetic field B at an angle theta with B, with the direction of magnetic field. Then resolving B into the rectangular components, resolving V into their components, V cos theta, number one, V cos theta parallel to B, and the second component, that is V sin theta perpendicular to B. So these are the two components of velocity V. Here let a positive charge be moving with a velocity V in a uniform magnetic field B at an angle theta. Now the force that is experienced by this positive charge depends upon some few factors. Writing here, the force experienced by the charge Q depends upon the first factor on which it depends, it depends upon the magnitude of the charge Q. What is the magnitude of the charge? The second factor on what force depends is the strength of the magnetic field B. If the strength of the magnetic field B is more, the force experienced by the charge also will be more. Then the third factor on which it depends is your perpendicular component, this one V sin theta. It depends upon V sin theta. These are the three factors on which the force experienced by the charge Q depends. If I mark this as 1, 2 and 3, then from equation 1, 2 and 3, we get force is directly proportional to Q, B, V, sin theta. Like this you will get it. And to remove the proportional sign, if you use a constant term K here, Q, V, B, sin theta. Now in SI unit, the value of K was found out to be 1. It is taken as 1. In SI unit, K is equal to 1. Therefore, force F is equal to Q VB sin theta. This is the magnitude of force that will be experienced by a charged particle when it is placed or when it is moving with some velocity v in a uniform magnetic field. Here some special case arises. Now you may be thinking why force depends upon v sin theta, why it does not depend upon v cos theta. Now you will come to know when you do the special cases. Case 1, when the charge is moving parallel to the field, and when the charge is moving parallel to the field, theta will be equal to 0 degree. The angle between this velocity vector and direction of magnetic field, if it is parallel, then it will become 0 degree. In that case, F is equal to Q VB sin 0 degree. Sin 0 degree value, you know it is 0. So it will be Q VB into 0, it will give us 0. That means the charge will not experience any force if you allow it to move parallel to the magnetic field. Then the second case, that's why you see here this V cos theta, the direction is parallel to the field. That's why the force experienced by the charge does not depend upon V cos theta. Now let us see about this V sin theta, why it depends upon V sin theta. Case 2, when the charge is moving perpendicular to the field, if the velocity vector is perpendicular to the field, then this angle theta will be 90 degree, then theta will become 90 degree. Then in that case, here you get sin 90 degree is equal to 1 So you get maximum force QVB. This is maximum value. So that's why this V sin theta, the force was depending upon V sin theta, the perpendicular component. Then to get maximum force, we'll have to make the charge to move perpendicular to the field. If it is perpendicular to the field, then the force experienced by the charge will become more. Then let us see the third case. When the charge is moving anti-parallel to the field, suppose you don't want to make the charge to move this side. Suppose the charge you are allowing it to move this side. The velocity is in this direction, the velocity vector is in this direction, and the direction of magnetic field is towards the right. Direction of the charge is towards the left. Then the angle made here will become 180 degree. Then in that case, theta will be 180 degree. And if theta is equal to 180 degree, then this sin 180 degree is equal to 0. So everything will become 0. That means if the charge is moving anti-parallel to the magnetic field, then also there will be no force experienced by the charged particle. Let us see the fourth case. When a neutral particle, let us say that it is not a charged body. If a neutral particle is allowed to travel with this velocity in the magnetic field, what will happen? Let us see. When a neutral particle is moving in a magnetic field with an angle theta, then what happens? Let us see. Then in that case, a neutral particle, it is not charged, so the charge will be 0. Then Q is equal to 0. It is not a charged particle. Then force experienced will be Q VB sin theta. This Q is 0, VB sin theta. Everything will turn out to be 0. So this movement of charge, the force will be expressed by a charged particle, not by a neutral particle, it says. Suppose the fifth case, let us see. When this charged particle just will keep in a magnetic field, not moving with any velocity, then also charge will not experience any force. That will be our fifth case, case 5. When a charged particle is at rest in a magnetic field, then what will happen? The velocity is not there, then it will be 0. It is at rest. Then also the force experienced will become 0. Then V is equal to 0, and the force experienced also will become Q B is 0, B sin theta. So everything will come out to be 0. That means the charge, if you just keep in a magnetic field at rest, it is not going to experience any force. It should move with some velocity, then only it will experience the force. Now the next topic that we'll study is, now it is clear to you, not only that, you have to know that you can write this in vector form as well, because sin theta is along with it. That will be your case number 6, you say, or we'll say it as in vector form. How we can represent. These are vector quantities. Force is vector, velocity is vector, magnetic field is vector. In vector form, how we can represent this force. If you write in vector form, Q is a scalar quantity, charge is a scalar quantity, we write Q, then these two quantities V cross B will come. You know that in vectors, A cross B is AB sin theta. So here VD sin theta will be V cross B. This is the representation of force in vector form. And this force is also popularly known as magnetic Lorentz force. This force is magnetic Lorentz force. It is due to the magnetic field. The force is produced due to the magnetic field. And this force we call it as magnetic Lorentz force. Now if a charged particle experiences force when you allow it to move in a magnetic field, then that force will make the charge to move. Like in dynamics you studied in class 11, an object at rest, if you allow force, then what happens to the object? It starts moving. If you allow some force, it will start to move. Like that here also, if a charge experiences force in a magnetic field when it is moving, then the direction, there will be some motion in the charge caused by the magnetic field. Now let us see in which direction the charge will move. Now let us study about the motion on a moving charge placed in the magnetic field. Now not force, already we know force is experienced by the charge. Now it should move. If it experiences force, it must move. Motion. Motion on a moving charge placed in a uniform magnetic field. Suppose I am taking the field like this now. This is perpendicularly downwards. If you see any structure of this form, cross marking, then you should know that direction of B is perpendicular to the plane of the paper. It is going inward. It is going inward. Here two cases will arise. If you allow a charge to move in a magnetic field, now how you are going to move? Suppose this is the direction of magnetic field coming this way. Then I can move in two different ways. One way is that I can allow it to come and strike perpendicularly like this, making an angle of 90 degree, or I can incline at some angle other than 90 degree like this. If I allow the charge to come parallelly, then you already know that it is zero. No force will be experienced. So these are the two cases we study now. If it comes and hits perpendicularly like this with some velocity v, then what happens? So this is your charge, suppose. Case 1 will write down like this. When V and B are perpendicular to each other, we know that this is your case. When V comes perpendicularly, the charge comes with some velocity V perpendicularly and comes and hits the magnetic field lines. If they are perpendicular to each other, we know that F is equal to QVB sin theta. This is the force that the charge is going to experience. And here in this case, if they are hitting each other at 90 degree, when V is perpendicular to B, we know that theta is equal to 90 degree. The force experienced by the charge will be maximum. This is maximum force. This is the maximum force experienced by the charged particle. Now, this force, in which direction it will move, that is the interesting part now here. You can use your Fleming's left hand rule. This stretch your forefinger, the middle finger and the thumb at right angles to each other. If the forefinger shows the direction of magnetic field and the central finger shows the direction of current. Now here charge is moving. Charge is moving. So moving charge produces electric current. So you can use this rule. If they are perpendicular to each other, the force experienced by the charge also must be perpendicular to both of them. As you already know that when we write V cross B in vector product, V cross B, then the resultant vector V cross B is VB sin theta. The direction of the vector will be perpendicular to both of them, V as well as B. Here also the direction of the charge must be perpendicular to both V as well as perpendicular to B. Now let us do and see. This thumb is the direction of magnetic field, like this. This is going inward. The cross markings going inward. Velocity, you are allowing it to hit perpendicularly like this way, going the velocity. You can see clearly, I think. I'll do a little bit like this. Can you see? This is velocity hitting perpendicularly with the magnetic field. Then the force will be towards the left hand side. The force will be towards the left hand side. This side it is showing. It is towards the left side. And then, the force is towards the left hand side if V is pointing in the upward direction, like this. And this force, as it is towards the left and B is going inward, this particle will start to travel in a circular path, like this. It will be circular. The charged particle will start to move in a circular pattern, and this magnetic force F will act like the centripetal force. It will act like the centripetal force. So it's simple to remember. You use your Fleming's left hand rule and can get the direction which side it will move. This force will move like this at every point. Suppose here if I take the charge now, then velocity it will point this way, force it will point this side. If I take the charge here, positive charge, then the same thing, velocity will be tangential like this and the force it will be towards the center. They will be perpendicular to each other. F must be perpendicular. F must be perpendicular to V as well as it must be perpendicular to magnetic field induction, that is B. It must be perpendicular. So what you have to know is when V and B are perpendicular to each other, it will experience maximum force and the particle, that is the charged particle, it will travel in a circular path. So this magnitude, you know now the direction. I'll write down here. F is QVB. That is your maximum force to be experienced by the charge, and the charged particle will travel along a circular path. The force experienced by the charged particle provides the necessary centripetal force for the charge to keep on moving in a circular path. To keep the charged particle in circular motion. Now let us see the second case. When V and B are not perpendicular, then what will happen? Let us see the second case. When V and B are not perpendicular to each other, if the velocity of the charge is not perpendicular to B, if the velocity of the charged particle is not perpendicular to B, then there will be two components. Here I will draw the diagram. Suppose in terms of x-axis, this is y-axis, this is z-axis. Suppose a charge class Q, this is the direction of magnetic field, say B, along x-axis. Then this charge, you are allowing it to travel along this angle theta, this is not 90 degree this time. Then what will happen is, this at this point the velocity is in this direction V. At this point it is in this direction. Then you can resolve it into the rectangular components. One will be V parallel component. I am drawing a parallel line, and one will be V perpendicular. V, this will be perpendicular. Both are vectors. This V perpendicular will allow the charged particle to still travel in a circular path, but this V parallel will push the charged particle towards the right, towards the direction of magnetic field. So two velocities combined together, the path of the charge, it will be a circular motion like this, but not in the same place like before. It will form a helix and move ahead like this. It will form a spiral path. The component V perpendicular will make it to move, as we know that if V and B are perpendicular to each other, it forms a circular path. Is correct. But this component V parallel will push along with the magnetic field direction in the forward direction, thereby forming a helical path. This path we call it as a helix or helical path. So this way it will start to move, forming a helix. The component V perpendicular, will make the charge to move in a circular path that means as in the first case, and the component V parallel will make the charge to advance in the direction of magnetic field. Thereby together the combined effect of V parallel and V perpendicular will make the charge to move in a helical path. The combined effect will make the charge to move in a helical path. Now in both the cases, in one case the charge moves in the same position in a circular path when you allow the charge to go and hit the magnetic field line perpendicularly, but when you allow it to hit with some angle, then it forms a helix and moves. It forms a helix and moves. So in both the cases, the motion is a circular one. So when a body is in circular motion, we know that it will have a specific radius. Here, suppose this is the radius r. Then if a body is in circular motion, it has frequency, how frequently it completes the circle and comes back to its own original position, frequency, angular frequency, time period, all these expressions we'll see now one by one. As the centripetal force required for circular motion is provided by the magnetic force centripetal force Fc will be equal to your magnetic force. The centripetal force, your expression is mv square divided by r, but which velocity makes to move in a circular path? Then we'll say that perpendicular component, that is equal to your magnetic force, that is qvb. Here also v is perpendicular, that's why sine 90 degree is equal to 1. And it's not necessary to write now, you already know for perpendicular component. This velocity you can cancel it out. R is equal to mv perpendicular divided by qb, and in terms of momentum, mv we write just linear momentum, p divided by qb also you can write. These two expressions, this one and this one, gives us the radius of the circular path. Now in terms of kinetic energy, if you want to write, this expression gives us this is the expression for the radius circular path. And this expression is applicable to both the first case as well as this case. The expressions, mathematical expressions are same for both because the circle that it will form will be the same. Now, if you know the radius, then you can find out the time period. Time period, or in terms of kinetic energy, in terms of kinetic energy, suppose K we are taking it as kinetic energy, then you know that momentum in terms of kinetic energy is 2mk. Root over 2mk is the value of momentum qb. You can express radius like this also. But you should know that this is a general expression. And when you do numerical analysis, here V perpendicular we are writing because here you have got two components. But in the earlier case you have only one velocity. So if you don't write this perpendicular also okay. But when you are deriving with this diagram, then it is necessary that V must be perpendicular. Now, to find out the time period, T is equal to total distance, it will be 2 pi r. The radius is r for a circle, circumference of the circle is 2 pi r divided by speed or velocity is v. Distance divided by speed gives us time. So in this expression you will get like this: 2 pi r, the radius will take this one mv divided by qb, and you have one v here, cancel out, you get the expression for time period. Time period T is equal to 2 pi m divided by q into b. This gives us the time period. Then what will be its frequency? Then how frequently it rotates? Then reciprocal of time period gives us frequency. Frequency nu is equal to reciprocal of time period, and this is qb divided by 2 pi m. And angular frequency, how much it is then? Angular frequency also we call it as angular velocity. Angular frequency omega is how much then? It is 2 pi the linear frequency. 2 pi linear frequency, you can see here it is qb divided by 2 pi m. 2 pi, if you cancel it, you will get the expression qb divided by 2m. So this will give us the angular frequency or the angular velocity of the charge that is moving in a circular path in the uniform magnetic field. Now, one more thing is there. Distance between these two loops, we call it as pitch. What will be the pitch? This distance from here to here. This we call it as pitch. So to calculate the pitch, write as P simply. This is a distance, linear distance from this point. If I write x, y, again there will be a problem. There is x axis, y axis. Pitch, let it be AB, A to B. That is our pitch here. Where I am writing it as P. Pitch distance is equal to speed equal to distance by time. Then distance is equal to speed into time. Speed, or we'll write as which speed will take, V perpendicular or parallel. It is going horizontally. V parallel is responsible to go horizontally. So it will be V parallel multiplied by the time period. The value of V parallel will keep as it is. Time period, you know the value, that is 2 pi m by qb. So it will be 2 pi m by qb into V parallel. This will give you the expression for pitch of the helix. So these are the few expressions that you have to know when a body is in circular motion, and you will have to know very clearly why it is moving, how it is going ahead. All these things must be clear. Now let us see the force on a moving charge placed in a uniform magnetic and electric field. Now, recently you have seen that force is experienced by a moving charge when you send the charge with some velocity in a magnetic field. Now, the combined effect of electric and magnetic field, what will be the force experienced by the charge if it is sent in a combined electric as well as this side electric field, this side magnetic field? Then what will be the condition of the charge? Actually, this force, combined effect of the force, we call it as Lorentz force, and this is applicable in a device called cyclotron. A cyclotron is a machine where we can accelerate the charged particle by applying both electric as well as magnetic field. But that topic is deleted for this year 2021 batch. But this topic you will have to know what is Lorentz force. You have to know. In static electricity you studied that electric field applied, electric field intensity is equal to force per unit charge, like this you studied. So this force is your electrical force. F is equal to Q into E. This is your electrical force. Now this electric force that will be experienced by the charged particle plus the magnetic force, what we learned earlier, that magnetic Lorentz force, the sum total we call it as, that is the sum total of both the forces will be experienced by the moving charge when it is placed in a combined field, electric as well as magnetic field. Electric force is equal to this QE. Let me write in vector like this. I'll write down. And magnetic force, we write it as Q V cross B. The sum total of both the forces, the electric force and the magnetic force, together we call it as Lorentz force. This is your magnetic Lorentz force, this one. And this is your electrical force. Together we call it as Lorentz force. So if I write Lorentz force F, then it will be the sum of the electrical force or the electric force and the magnetic force. The sum total of both we call it as Lorentz force. This is your Lorentz force. Directly it is written in vector form. If you write in scalar, here there will no change QE, but here cross product is there, so it will be QVB sin theta that will come. Then this force we call it as Lorentz force. So if it is asked like exam, what is Lorentz force, then you should be clearly be able to say that the sum total of both electric as well as magnetic force we call it as Lorentz force. It is expressed as, then you can write down mathematically, F is equal to QE, that is for electric force, and QV cross B, that is for magnetic force. Now let us see the motion of charged particle. charged particle in combined electric and magnetic fields. This is also known as, this heading we can term it as velocity filter, or in some books you'll get it as velocity selector. So velocity selector means you can choose the velocity with which you allow the charge to move in a magnetic as well as in a electric field, combined magnetic as well as electric field. Generally magnetic field, electric field, they are perpendicular to each other. Now to know this, we'll start like this. Lorentz force F is equal to QE plus QV cross B. If we consider the electric field E, the magnetic field B, and the velocity of the charged particle perpendicular to each other. Suppose if electric field, magnetic field and velocity, they are perpendicular to each other, then we can consider our coordinate axis. Let us take the velocity along x-axis. This is along x-axis. So V I cap I can write. Then let us take the electric field along y-axis. E then become j cap. And magnetic field will take along z-axis. That is your y-axis. This is your z-axis. This is your B K cap. You can write like this. The direction of electric field is this way. Magnetic field is this way. These are all vectors. And then velocity direction is towards x-axis. If you take like this, the origin, if I write here, then from this expression what we can write is, here what we have taken, electric field, we took it as E j cap along y-axis, E j cap. Magnetic field we took along z-axis, so this is B k cap. And velocity we took along x-axis, so V I cap. If you represent like this, then your Lorentz force F can be written as Q E j cap. This is E, we are writing it as E j cap, plus Q V is V I cap, cross B is B K cap. Then in this case, you'll get like this Q E J cap. Q, here you can see I cap cross K cap. This I cap cross K cap. You're coming like this. It's clockwise. I cap cross K cap will give you J cap, you know, but will it be positive or negative? You learned in class 11. If it is clockwise, negative. If it is anti-clockwise, then it will be positive. But here you can see very clearly I cap cross K cap. It will give you a negative of J cap. So this is V B minus J cap. And write down here especially, since I cap cross K cap gives us minus J cap. Now this one can be written as QE J cap plus into minus is minus Q VB J cap. Now here you can see the term Q is common. E minus VB J cap is also common. From here what we know is if E is bigger, then it will be a positive quantity, and E J cap, then the force will be towards positive y-axis, that is force due to this electrical force will be in the upward direction. And if QVB, this magnetic force, is bigger, this Q is taken common here, QVB, if it is bigger, then we know that the result will be negative. Negative of J-axis means it will come down towards, negative of Y-axis will come like this, force magnetic will come like this. If we can adjust these two forces, the electric force and the magnetic force, in such a way, if these two values are equal, I'll write down here. If we can adjust the two forces, electric force and the magnetic force, such that both the forces are equal, then the charge will move in the combined field undeflected. So the electric force also must be exactly equal to the magnetic force. Then the charge will move undeflected. It will neither go this side, it will not go this side. It will remain undeflected. It will move in a steady path. So in such a case, if both the forces are equal, then your QE must be equal to QVB. This one Q into E, QE must be equal to QVB. This is your electrical force and this is your magnetic force. You can take from here. In this case, QQ you can cancel it out, and this ratio V is equal to E by B. So this velocity will tell you, or at what velocity you have to send the particle in electric and magnetic field, combined electric and magnetic field, so that it will move in a steady path. It will not get deflected towards magnetic field, it will not get deflected towards electric field. This formula will tell you. So before you send the particle, you will have to know at what velocity you should send. So to know the velocity exactly, first we'll find out the ratio between electric field and magnetic field. These two values, if you know, you will find out the ratio, then you get the velocity, and you will come to know at what velocity you can send the particle in combined electric and magnetic field. That's why this velocity we call it as velocity selector as well, or velocity filter as well. Thank you and have a nice day. Stay tuned with LFI Educates.